So today I'm going to be talking about a system called Clipper that we've been building to do low latency, high throughput prediction serving for machine learning. And this is joint work with a bunch of awesome careers, all the way from undergrads up through senior faculty. So generally, when people talk about learning, and you can see where Jan got some of his slides this morning, they talk about sort of when they talk about machine learning, they talk about sort of the training process. And even Ray, is mostly focused on how to build these machine learning models, how do you build reinforcement or train reinforcement learning policies. And generally, this looks like take some large data set and use it to train some complex model. Or in the reinforcement learning case, it's not necessarily starting with a big data set, but starting with doing lots and lots of simulation runs, train a policy. And the result of this is some trained model that sort of at its simplest is just some function that takes in a query and produces a decision. For example, it might take in an image and try and tell us what's in this image. And although sort of in the future we see that maybe supervised learning isn't going to be sufficient for all cases, this is actually like a pretty powerful tool in and of itself. Just being able to build models that make useful predictions in a supervised context is useful, and there's a ton of people who are struggling to get even their simple machine learning models into production. So I don't actually think it's a solved problem. And that is what I'm going to be talking about today, is this process of taking the model that you've trained and actually getting it into production, being able to do something useful with it. So the new queries come in, we can use this model to make decisions interactively in real time. So that's what Clipper focuses on, and that's going to be the focus of my talk today, is this serving process. And in particular, I'm going to be focused on prediction serving for interactive applications, which means that we need to be able to deliver prediction within the window of human response time, which is on the order of a couple hundred milliseconds, which means that our end-to-end interaction can only take a couple hundred milliseconds, so our models need to be about an order of magnitude faster than that. So in this talk, first I'm going to talk a little bit about some of the challenges of prediction serving, particularly from a systems perspective. Then I'm going to give an overview of Clipper and talk about its architecture and some of the design decisions that we made. And then I'm going to wrap up talking a little bit about how you can actually deploy and serve models with Clipper today, and some of the issues that we ran into and how we solved them when transitioning from sort of an academic system to a real system with real users. But first I want to argue that prediction serving raises new challenges. And in particular, I want to highlight two. The first is the need to support low latency, high throughput workloads. And the second is the ability to manage and take advantage of the large and growing ecosystem of machine learning models and frameworks. So let's dig into these quickly. So what's challenging about supporting these serving workloads? Well, for one, models are getting more complex. This is, I think, the architecture of GoogleNet. It's like a 23-layer computer vision model. It's fairly expensive. It was actually designed to be a lightweight state-of-the-art computer vision model, state-of-the-art as of like 2015. It's a couple years old at this point. But the high-level bit here is that models are getting really complex. They're getting really expensive. They can take tens of gigaflops, or tens of billions of floating point operations to make a single prediction. And they're being deployed on the critical path. People want to use these models to make decisions between a user clicking on something or starting an interaction or speaking and the end result, which means that we need to maintain latency SLOs even under heavy workload. We care about tail latencies a lot. So as a result, people are using specialized hardware to support these applications. For example, I really like this example. If anyone's used Google Translate, it works really well. This is a state-of-the-art machine translation system, and Google has published some papers about how this system actually works internally and the models that they use and the cost of using those models. So if we look at the serving workload of Google Translate translates somewhere in the ballpark of 140 billion words a day or 14 billion sentences a day. And if we take the numbers that they report in their paper on how this model works, that would take about 82,000 GPUs running 24/7 just to handle this workload. This is pretty expensive. It's also really power hungry and energy inefficient. And so Google actually developed new hardware. They developed these tensor processing units, which is a custom ASIC that Dave Patterson helped them design and develop just to reduce the energy cost and the time to serve these inference workloads with these really complex state-of-the-art models. And while not every company is designing new hardware, this sort of approach of taking a big hammer and using it to solve a really high-value problem is indicative of the way large companies are building machine learning applications. They're building one-off systems that support, a particular use case, a particular model. And that makes sense because these models are sort of the core value of these companies, of these products. And so it makes sense to spend a bunch of time and engineering talent on building these systems. But it's sort of fundamentally unscalable. In particular, these systems are expensive to build and maintain. Even if you have the engineering time, it adds a lot of friction to the sort of iterative data science and model development process. If every time you change your model, you have to change the code that runs that model and the systems that run that model and debug it all and put it through performance testing and stress testing and things like that. And this happens because people are building these highly specialized systems where the system and the machine learning are tightly coupled. So it's difficult to deploy and change, and it requires the cooperation of data scientists and engineers, and sort of all of these people that shouldn't fundamentally need to be working together just to deploy machine learning. And often they only support a single machine learning framework, which makes sense if you're in Google or something and you're going to dictate that everyone uses TensorFlow. But we think that we should build general purpose flexible systems that can support this whole ecosystem. So that leads me to this second challenge that I want to highlight. How do we actually take advantage of this large and growing ecosystem of machine learning models and frameworks? So why does this sort of fractured ecosystem exist in the first place? Well, a big reason is that people are using machine learning for a lot of different things, and they're using different tools to build models for different applications. For example, if I have fraud detection, I want to build some large linear model on some massive data set. I might use Spark and its ability to do distributed training to train this model. If instead I want to bring in a computer vision model or some NLP and bring in a deep network, Spark isn't going to be sufficient. I might want to bring TensorFlow into the mix. So already, with this application and its evolving requirements, we might have multiple machine learning frameworks that data scientists want to use to develop this application. And then, of course, we don't just have fraud detection applications. So we have two machine learning frameworks. They specialize in different things. We're already running into problems. TensorFlow is written in Python and C++. Spark is JVM based. Those are hard to make work together. And they also require different hardware. You probably don't need to run your Spark model, your large linear model, on a GPU, and the code probably isn't optimized for that anyway. But you're almost certainly going to want to run your computer vision model on a GPU or a TPU in order to meet your latency SLOs. And then you also have different hardware costs, and you have to scale things differently. You might have to have a lot more replicas and a lot more hardware thrown at your deep neural network than at your simple linear model. And then, of course, the situation just gets more complicated as we add more frameworks and more applications. And the end result is sort of this many-to-many dependency structure that sort of just happened as a sort of historical artifact. There's no fundamental reason why these applications and these models need to have these tight dependencies. But because they have these tight dependencies, we run into problems. If you're not a big company and you can't afford to take a whole engineering team and build a new serving system for a new framework, you're sort of stuck with open source systems and sort of what off-the-shelf software gives you. So a pretty common approach to this is to score these models ahead of time offline. And this looks like basically an extension of your batch analytics system. So if you're already using some sort of batch analytics framework like Spark to train your model, you can just extend this to pre-score all the predictions you might need ahead of time. And then you've transformed your prediction serving task into a data serving task. And we know how to do low latency data serving. There's lots of great databases to do that. And at serving time, all you need to do is look up the decision that you've pre-computed. But as should not be a shocker to anyone in the room, there's a bunch of problems with this as well. So one is that it requires the full set of queries that you might need ahead of time. And this basically makes it fundamentally incompatible with most of the machine learning applications that are in use today. If you're doing, recommendations on a small fixed catalog and you don't want to do a lot of personalization, this could work. If you don't have hard interactivity requirements and you can afford to detect fraud a few hours after the credit card transaction went through, this might work. For most other things, anything where you're trying to do machine translation, any interactivity, any personal assistance, anytime where you're trying to detect fraud before it costs you a lot of money, at the point of sale, this won't work. Even in situations where it does work, you end up with a lot of wasted computation and wasted space because you're pre-computing the set of possible decisions that you might need rather than a more lazy approach. And finally, it's costly to update because anytime you want to change anything, you have to sort of recompute the whole set. So these are sort of the two most fundamental challenges that we identified when trying to sort of figure out how do we make prediction serving easier. There's lots of other challenges as well, but if you can't solve these two, you sort of you have nowhere to go. And so what we asked was there's sort of pros and cons to each of these approaches that I outlined. There's a reason that people are taking both of these strategies. We have these highly specialized systems for specific problems. We have offline scoring that uses existing frameworks and systems. Can we unify and extract the best things from each of these approaches and get the best of both worlds? And that's exactly what Clipper aims to do. So how does it do this? Well, if we start with this sort of diverse ecosystem as sort of a fact of life and figure out, all right, how do we encapsulate and decouple these applications from these models? The first thing that you probably want to do is sort of encapsulate each of these frameworks, each of these models, and maybe give them some sort of uniform interface. Hide all the differences from these applications. Then, once you've done that, you probably want to stick something in the middle because while you might be able to hide them behind a uniform interface, they're not all the same. The way that you route and load balance and queue your deep network running on a GPU or a GPU cluster is going to be different than the way you deal with your massive random forest. So you probably want something in the middle that sort of can account for these differences without the applications having to deal with it. And then you want some uniform interface that the applications can query as well. And that's what Clipper is. It's the thing in the middle that figures out, that encapsulates all of these models, along with all of the other things that you need to actually deploy machine learning into production, like featurization and post-processing, and then automatically figures out how to account for the differences, the performance differences, the hardware requirement differences of these different frameworks. At its core, Clipper is, it's a system. It's about 10,000 lines of C++, some library code, some Python code. It's open source. And what we want is sort of a community-owned platform for model deployment and serving. And we think that there's a lot of value in developing in a system like this coming from an academic lab, a research lab, rather than sort of a company that has a lot of vested interest in a particular framework winning out. I'm hopeful. I know that, among others, Facebook and Microsoft today announced some tools for compatibility between PyTorch, which is developed by Facebook, and Cafe2, which is also developed by Facebook, maybe, and CNTK, which is developed by Microsoft. And sorry, Sarah's in the audience giving me cues. And Apple announced CoreML a few months ago, which allows you to take models trained in different frameworks and stick them into iOS. So we are seeing some compatibility, but we're not seeing sort of a serving system that deals with more than just making models API compatible that doesn't have a vested interest in any particular training framework pointing out. And the reason that I think actually, I called it a fractured ecosystem, but that having this diverse ecosystem is really important, is we're developing lots of different tools that are good for different things, and we shouldn't tie people's hands, we shouldn't tie the tools that they use to develop models based on how they're going to be deployed. We should let people use the best tool for the job sort of across the whole process. So what does Clipper actually look like when you run it? Well, from the application perspective, Clipper has a REST front end or an RPC front end that you can query. And when an application sends a prediction to Clipper, that goes to this query processor. There's some other stuff that runs as well. In your tutorials, you'll see sort of what a running Clipper instance looks like and see all the different Docker containers involved and stuff. But Clipper is also stateless so that we can scale out, and all of our data is stored in a persistent database. And then when you actually deploy models into Clipper, these things all run in their own separate Docker containers, and I'll talk about how that works a little bit, that are then communicating with this query processor, which is doing load balancing and queuing and other things like that. And by separating things into different Docker containers, we get this encapsulation. And then finally, you can manage it all and administrate it from your laptop or from a Jupyter notebook, as you'll be doing in the tutorial. And then sort of the fundamental goal of Clipper is to be able to connect analytics and serving. So it's great that you have a system that can serve machine learning models, but it's really important that you actually be able to get your machine learning models into Clipper. So the other piece of this project is figuring out ways to bridge analytics and serving and make it easy to get not just models, not just your serialized TensorFlow model, but all the things that went into actually making a prediction, from featurization, database lookups, post-processing, filtering, all these other things that you need to do to prepare your inputs for a model and to process the result of that model's prediction, and how to get that whole thing into the serving system. To get started with Clipper, because it's in C++ and dealing with C++ compilation, things like that can be a little bit finicky, we distribute everything through Docker, which actually has some added benefits, which I'll talk about in a second. And then, so basically all you need to do to get started with Clipper is pip install Clipper admin, which is that little piece, that little library that runs on your laptop, and that will automatically pull down and manage these Docker images and sort of deal with all that. So you don't need to compile anything to get Clipper running, which is really nice. So now I want to briefly talk about some technologies inside of Clipper and how we use them to achieve this goal of a flexible, high-performance, general-purpose prediction serving system. So one is how we containerize frameworks and what that provides us, which is essentially a unified abstraction and process isolation. Then I'm going to talk a little bit about how we do cross-framework caching and batching to optimize the throughput and latency. And this is the piece that accounts for the physical performance differences among these different machine learning frameworks while still treating them with the same interface. And then finally, I'm going to talk a little bit about how we actually enable cross-framework model composition and how we can use things like ensembles and bandit methods and stuff like that to improve the accuracy of your models in production. Now, this last piece isn't in the Clipper open source system yet. There's still some research that needs to be done around sort of the right way, the right programming primitives to expose in order to provide this power and this flexibility to users without giving them so much rope that they hang themselves with it. Which was, we actually had it in, and then people were getting confused, and so we ripped it out so we could do it better. Okay, so let me talk about Docker and how we use Docker a little bit. And then I might skip ahead a little bit because this talk is running long. So this is sort of the picture that you should have when you think about Clipper. You have models running in their own model containers that are Docker images. They connect to Clipper over an RPC, a lightweight RPC system, and then applications never talk directly to models. So one advantage of this is that it provides a common interface to simplify deployment. By putting things in Docker images, we let you evaluate models and all of this code around models using the original code and systems that were used to develop the models. And this is important because by avoiding this translation layer, or only using rigorously vetted tools that will automatically, extract a model into Core ML or whatever, you avoid sort of a lot of the surface area for bugs that can occur when you, accidentally mistranscribe some default hyperparameter setting that had one value in one system and a different default value in the system you're translating to. And these are bugs that happen, and they happen a lot. So in order to achieve this container-based deployment, if you want to deploy a model to Clipper, you implement this simple model API. It basically has two methods. There's an initialization method that tells you how to, that tells the model container how to take a trained model that was saved somehow in some persistent format and unserialize it, deserialize it. And then the second function is, given a set of inputs, how do we make predictions with this model? The reason that this interface is predict batch, not predict, is to allow for these micro-batch optimizations that can dramatically accelerate performance, particularly when you're using models that run on GPUs, which have massively parallel, a lot of parallel cores. Once you've implemented this model API for your model, your application, and we have API support for this in several different languages. We have Python, Java, C++, and actually we'll have R support in tomorrow. The PR is under review right now. It should be in by the end of the weekend. You package this model container implementation along with all of the dependencies for your model. For example, this Spark binary, if you're deploying a Spark model, into this container. And because it's a Docker image, it's this self-contained, packageable environment that you can then distribute. Once you have this model container, you just connect it to Clipper with this RPC system, and then Clipper can route queries to it. And because we have these models running in their own Docker containers, we can connect many models at once to Clipper. Now, this Dockerization has some additional benefits as well. Beyond just providing a common interface, it also provides process isolation, which is particularly important because some of these cutting-edge machine learning frameworks sometimes have bugs in them, and they result in seg faults and kill your process, and you don't want that to sort of kill your whole serving system. You want to isolate this possibility as much as possible. And then it also provides a convenient mechanism for scaling out your models. If I need more throughput because I have some expensive neural network, I can just replicate that model container. It's a Docker image. I just start another one, and now I have sort of linear horizontal scale out. I'm going to skip ahead a little bit because I'm running a little bit low on time. And the next thing I want to talk about is the cross-framework caching and batching that we do that allows us to automatically adapt to the latency constraints of applications while maximizing the throughput of all of these different types of machine learning models that are often performing fundamentally different types of computation. So inside Clipper, inside this core process, we have a couple pieces. We have a cache, and then we have this latency-aware batching algorithm that's running. And this is useful because, well, for a few reasons. So one is that often prediction serving workloads are bursty, and they come in batches. If you're trying to load a page for someone, and you're trying to predict what to put on that page, and you have to put 10 things on that page, you're not just making one prediction, you're often making many predictions. They all come at once. And then the other piece is that a lot of these frameworks are actually throughput optimized. And what they do to improve throughput is take advantage of data parallelism in the prediction process. They're often written to actually run on hardware that's massively parallel, like GPUs. And so we get really nice throughput scaling as we increase the batch size. But in order to take advantage of this, we need to know, the optimal hardware configuration, how the model and framework are performing, and even the system load in order to find the right batch size. And And the other thing is that Clipper is designed to serve interactive serving workloads. This means that we need to meet latency SLOs, which means that maximizing batch size to maximize throughput is going to be really problematic if it's leading to queries that take 2 seconds to run. So we want to do batching, we want to maximize throughput. We want to do it in a latency-aware way. So the way that we do this is to basically adaptively trade off latency and throughput on both a per model and a per application basis. For example, one algorithm that we use is that given a latency constraint for an application, say my application says that it wants requests within 50 milliseconds. Well, I can adaptively increase the batch size additively until I hit that latency objective, until increasing the batch size further means that requests take more than 50 milliseconds to be processed. I know at that point, even if increasing the batch size would improve throughput, that's not an option for me. So then once we've exceeded it, we can multiplicatively decrease and sort of dynamically find the optimal batch size and vary it based on system load and workload and things like that. And as it turns out, this is actually massively useful. So one reason why this is useful is because we've stuck in this additional RPC call, and batching helps amortize some of these network overheads. But another really big reason why this is helpful is because of these existing data parallel optimizations that many machine learning frameworks implement. So now I'm going to skip ahead to some of the lessons that we learned from deploying models with Clipper, and then we'll get you started playing with Clipper and running through the tutorials. So I've hinted at this a couple times in the talk already, but one of the goals of Clipper is not just to be able to do high-performance prediction serving, but also make it really easy to deploy models into the serving system, into production. And so we want to make it easy to connect your analytics and your serving system. So I'm going to talk a little bit about how we deal with this arrow, getting models out of your training process and into your serving process. So as I talked about before, you can always implement your own model container. And we did put a lot of time and effort into sort of making this interface as narrow as possible. But after doing this, we realized that it still sort of involves writing a Docker container, writing a little bit of additional code, and so we asked, can we do better? In the training process, in the training system, you already have all of the code to make predictions, because making predictions is a fundamental part of basically any machine learning training algorithm. You need to know how well you're doing in the optimization process in order to optimize it. And so what we did is we wrote some code to make it easier for common cases to sort of sidestep all of that and go directly from the model in your, for example, your Spark driver program, directly into the serving system without having to figure out how to serialize the model, how to write a Docker container, having to launch a Docker container, but just being able to call clipper.deploy and with the model function object itself and get it directly into a model container. And this actually makes things much cleaner. And you'll get to play with this a little bit in the tutorial. Now, that seems like it's actually not that hard. What's the problem here? And actually, the big problem that we ran into is that models don't run in isolation. It's not enough to just serialize the Spark model or the TensorFlow model and deploy that into production. Because there's inevitably pre-processing, featureization, feature extraction, image cropping, whitening, all of these things. And then post-processing, often application-specific logic. People want to do filters. They want to include business-specific or application-specific policies. And all of this code is not independent of the model. You can't swap out the model and leave a lot of this code the same. This stuff all needs to be versioned together and treated as a single unit. And so in order to actually effectively be able to deploy directly from the training system to serving in production, you need to empower people to both deploy the model that they train and all of this other important code all in one unit. So what we've done is we've started to develop a library of what we call model deployers that automatically and intelligently save not just the model itself, but all this wrapping code. And we do this by using sort of existing programming language functionality to do automatic dependency tracking, code serialization, things like that. It's sort of an ongoing battle, but we've made a lot of progress, and you'll get to play with that. And the idea here, and the reason there's a library and not just one per language, is that you need to be able to capture framework-specific models that are often serialized or saved in one way, and arbitrary code that that's doing the pre-processing and the post-processing that's captured in a different way. And you need to capture that all together. Once we've done that, then we can replicate the entire training environment, but selectively replicate it. So we're not going to copy all of the training data that you've loaded, but we'll copy all the dependencies that you need to make predictions and load that replicated environment in a Clipper model container automatically. And you'll get a chance to use some of these in the Clipper exercise. So right now, we have in Python, we have support for scikit-learn and PySpark models and arbitrary pickleable Python code. And we're working on adding support for TensorFlow, Caffe2, Keras, some of these other frameworks, sort of on demand. But the nice thing is these model deployers are fairly lightweight. In Scala and Java, we have support for doing this with Spark. And then we have a pull request that Corey, my fantastic other lead developer on the Clipper project, wrote that will be in by the end of the weekend that uses our sort of really nice functionality to track down all these dependencies and stuff. The last thing I'm going to mention is that the goal is to connect analytics and serving, and so we can't neglect the serving piece. And so as Alexei mentioned in his intro talk, we just added support for running Clipper in Kubernetes alongside all of your other applications. And this is sort of the right way to deploy Clipper in a production serving environment. And Kubernetes sort of makes it really nice to scale these things, to have fault tolerance, to have health checks, to do custom networking. And so now you can you'll be deploying Clipper just on a local EC2 instance in the tutorial, but it's basically a one-line code change to deploy to a running Kubernetes cluster instead. So we're pretty excited about that as well. So let me wrap up. Our website is clipper.ai, and feel free to check that out. There's a couple links to the documentation on our website throughout the tutorial. 0.2 will be released right after RiseCamp. I didn't want to try and deal with getting the tutorial debugged and working and cut a new release at the same time. So as soon as your tutorials are done, I'm going to go cut the release. And in fact, the first release candidate is already up on PyPy and Docker Hub. We're actively working with early users, and we're looking for a few more early users. So if you have use cases that you think would work well with Clipper, please talk to me or send me an email. And then we have a mailing list. You can post issues on GitHub. And then coming up in the next couple months, we're looking to expand this library of model deployers, continue to make it easy to deploy models into Clipper, improve model and application reliability and debuggability. We have some ongoing research to study this that's going to use the Ground project as well to sort of capture a lot more of the semantics of the models and the data and the code that you're training to try and find problems before they occur and help you identify new problems as they crop up. And then we're still working on implementing and adding support for bandit methods and online personalization, integrating with some of the Cascades work that we have going on in the lab as well. And you can check us out on GitHub. So that's Clipper. I have time for some questions because the Clipper tutorial is actually fairly short. But before I take questions, why don't I get people oriented with the tutorials. Anyone who wants can just get started on them. And then I'll be circulating around, but also stay up here for a couple minutes if people want to ask questions about the talk. So most of you were here this morning to run through the Ray exercises. So the process is exactly the same. Do I want to do it? No. my internet was a little bit spotty. I'm not connected to your network, so hopefully yours is all working fine. But you'll log into risecamp.tech, just as you did before. You'll see your Jupyter notebook. Instead of clicking through to the Ray exercises, click through to the Clipper exercise. There's only there's 2 notebooks in that directory actually. You want the notebook that says Clipper_exercises. Once you click into there, everything else is totally self-guided. You don't need to worry about opening up any of the other files or directories or anything. And you should sort of be able to get going straight from there. All right, cool. Let me take some questions now. Yeah. So that's a really good question. We're actually, we have a project that's building on, to rephrase and to get it on the microphone, the question was, if I have multiple machine learning models that I'm using to make a prediction, a single prediction, but there's some sort of sequential dependency, and so I need to take the output of one and feed it into the input of another, how would I do that with Clipper? So right now, with the system that you're going to be playing with today, the way to do it is to do that rerouting in your client application. But you've totally identified a really common pattern and something that we're working on supporting. In particular, what we're working on and what we have a prototype of that's not in the open source system yet, but we're pretty excited about, is basically a high-level sort of semi-declarative language that will and when I say language, I mean a simple Python API, that will let you specify these dependencies and then deploy these models into Clipper. And then the cool thing is that if we have sort of global knowledge of this computation graph, we can extend these ideas around batching and queuing and resource allocation to these multi-model computations and figure out, all right, for this application, with these latency objectives and this expected workload and these models in it, you're going to want to allocate 4 GPUs for this model and 7 hyperthreads for this other model, and Clipper will automatically make sure that we do sort of global joint queuing and load balancing and routing and things like that, so that we meet your end-to-end latency objectives and sort of across these frameworks. So stay tuned. It's actually a really interesting and has turned out to be a pretty interesting research question as well. But yeah, you'd have to do that yourself right now.
Okay, I have a follow-up question.
Sorry, I can't. Oh, there you go. Thank you.
So if I understand your architecture right, the Clipper is a layer between the application and your models.
Yes.
And I wonder how you compare with, like, let's say they have the TensorFlow serving, right?
I skipped that slide for time.
No, let me just finish. So the TensorFlow serving was designed to try to support multiple different kind of models. I think it's my understanding TensorFlow serving, for example, supposed to be able to support, at this moment, Caffe models and TensorFlow models. Right? Okay. So I wonder, why you take a completely different approach and try to understand, because you are introducing another layers on top of it. So it must be introduced more latency.
Right. So TensorFlow serving takes a sort of fundamentally different architectural approach, where they run everything in the same process. And so in order to add support for a new framework, you need to basically link against it. I don't know what the current status of TensorFlow serving was. The first pull request, which was like maybe a year ago, a little bit less, to add Caffe support to TensorFlow serving, was a 3,000 plus C++, 3,000 plus line of code C++ pull request required writing a ton of code, a ton of integration. You need to get all these things to get linked together. That also relies on the fact that Caffe is also written in C++ and can actually be compiled to a shared library and linked in the first place. So the sort of design constraint that we imposed on ourselves was we want to be able to manage, or to be able to serve models trained in all of these different frameworks, including frameworks that are written in Java, that are written in R, that are written in other weird, obscure languages. And the only way that I know to guarantee that type of cross-language compatibility is by interposing an RPC request. So that's one reason. The other reason is that we actually wanted to understand, we did impose another layer of indirection. We wanted to understand for sort of the use cases that TensorFlow serving targets, which is serving big, complex, deep neural networks. What is the overhead of this additional layer of indirection? And basically, we found that it's pretty minimal, because when what you're doing is serving these big, heavyweight computations, you can sort of hide the latency and hide the overhead of everything else within this computation with careful engineering. These numbers are reported there from our NSDI paper, which was a different version of the Clipper code base. So our current open source version isn't quite this fast, but we have a bunch of performance improvements coming down the line. But the summary is that we wanted to be more general purpose than TensorFlow serving was, and we wanted to make it easy to add support for new machine learning frameworks. And we didn't see a huge performance downside in our evaluation. I'll be circulating around, and I'll be around the rest of today and tomorrow. We should probably get into the tutorials and get started actually playing with the system. Thank you.